Hey everybody, Professor Heiman here for IBUS620, Research Methods in International Business and Markets. I want to talk about a topic that we don't cover in the class specifically, but I mentioned here and there. And this is going to be an introduction to dichotomous dependent variables. I'm going to switch up to the board here. And this assumes that you have some knowledge of some of the notation and conventions of ordinary least squares regression or multiple regression, if you will. So I'm going to start up here, dichotomous dependent variables. In this case, we mean binary variables. Here's some examples. They can take on one or two values, and that's it. For your outcomes, 0, 1, which is how we code them, white, black, yes, no, likes, dislikes, chooses, skips, or probably more commonly chooses, does not choose. Dichotomous dependent variables are pretty handy because they allow us to model people's choices. And so example would be, what color car can we predict people will want more of based on some prior data? You could be choosing between, do we manufacture cars in red color or a green color? And that's a dichotomous choice, just like the other examples. It's called logistic regression. It's also called Logit for short, which is what people generally refer to the technique as. It's related to ordinary least squares regression, so we can explain it in terms of OLS regression a little bit. And I want to talk about notation first, because that's like half the battle, is getting the notation correct. So I'm going to start down here, and we're going to let this term beta I xi just represent this longer term here, in particular, beta 1 x1 plus beta 2 x2 plus ... plus beta I xi plus some constant, and we're going to let beta I xi just represent that whole expression there, actually including the constant. It's an abbreviation of the long expression, so I can toss this around casually without having to write this out every single time I refer to it. And it's essentially the collection of the actual reality that we want to predict. Okay, it's the population parameters. They're capital beta, capital X, and so we know it's population parameters, and we want to calculate those, but we're going to estimate them from our sample. But what this stuff represents how the world actually is, how the reality that we're trying to uncover by taking a sample and running some statistics on it. So beta and X, capitals both, are population statistics. We don't typically know those. We're trying to estimate them. And we're estimating them by calculating B for the betas. Those are the actual calculated coefficients, and X, we're using our data, small x. So B is the calculated coefficient, and X is the data that we collected. That's the notation convention we're going to talk about here today. So slipping back over here, what does Logit do? It calculates the probability of a binary outcome, 0 or 1, and you put data in, and data would be your independent and your dependent variable data that you gathered. And Logit processes, much like regression processes, output estimates, BI, and these estimates are of the beta i's. Pretty simple, and that's what we're seeking, is a model that has some predictive power given the data we have. So putting it just a tad more formally, and I'm not a mathematician and I'm not a formal modeler, so I'm using notation that I believe you will understand, not notation that is necessarily the proper mathematical notation. I'm changing the notation into something else to make it more tractable to your comprehension and for my ability to express these ideas. So we're seeking to estimate beta i's, where we're calculating BI's, and so the fundamental relationship we're working for is the probability that the small yi equals the big yi, where the small yi is the data outcome, and this is the actual outcome in the real world, the capital. So that probability equals e to the bixi over 1 plus e to the bixi, whereas bixi is just the same as this, except with b's and small x's instead of betas and capital X's. So that's the data and the calculated coefficients. We're trying to calculate those, and it's e to the bixi over 1 plus e to the bixi, and we're going to call this, again for notation, we're going to call it a function, L of bixi, just so it's easier for me to write. And this function here looks like this. Okay, you have a probability on one side, on the y-axis, a probability that the data outcome equals the actual outcome in reality, and on the x-axis you have the beta I xi. The bi xi, and this is a good way to think about probabilities because the function is symmetrical. We like symmetrical functions. The outcomes are always in the inclusive interval 0 to 1, which is a result that is a good probability. It's very compatible with thinking of those outcomes as probabilities. And so this is also convenient because this logistic distribution, or the Logit distribution, it's a distribution that we want to use to calculate one or two-tailed tests. And this is great because it's symmetrical. Now, just shooting back over here for a minute, let's talk about a couple of the things that you can and can't do with the results of a Logit analysis. It's okay to compare the coefficients within a model, but not between Logit analysis models. Okay, that means you do one Logit analysis and you can look at the coefficients, magnitudes, and signs inside one model, but not comparing those to some other model that you calculate with a separate analysis. All right, so given that, to think about the answer to this question of what about the probability of our model being good, this is essentially of our estimated outcomes equaling our actual outcomes in the population. We could calculate that probability and we get a number between 0 and 1, but we usually don't. We usually just look at the coefficients like the normal distribution, just like as we do for the normal distribution in linear regression, but we could plug the data and the calculated betas, the calculated B's, the estimated betas, into this and get the actual probability. Again, we don't, we look at the coefficients. So a couple more final notes about logistic regression. It's handy because, again, you can calculate the probability of an outcome when you have outcomes that are measured with only two values, dichotomous values. They also call it discrete choice, binary discrete choice. All these terms mean the same thing. We kind of abbreviate the technique, and usually the commands in the software that you're using are the word Logit. So this is just a quick introduction to Logit. I'm not using necessarily proper mathematical conventions everywhere I'm doing this. I'm trying to create a small bit of intro material that allows you to understand what's going on in a fairly straightforward manner. That's it. Thanks for listening, and go Gators.